To introduce the team, I'm Harry.
I'm Alex.
I'm Faden.
I'm Jamie.
I'm Kiki.
And I'm Ollie. And we are the team behind ALADDIN.
Hello and thank you to everybody for being here for our project presentation this afternoon. We would like to introduce our product, the Anatomical Landmark Detection and Demonstration Interface, or ALADDIN. ALADDIN is a platform enabling the automatic detection of human anatomical landmarks using reinforcement learning with an integrated graphical user interface. This can be seen in the GIFs provided in the slide. Our presentation will begin with an outline of the problem we are trying to solve and our motivations for doing so. This will be followed by a brief overview of the software engineering techniques pursued by the team. We will then provide a demonstration of ALADDIN in action and talk through the various features of the GUI, as well as technical details of our implementation. This will be followed by a section on human-in-the-loop reinforcement learning. This will include the theory and our motivations for using it, details and a demonstration of our implementation, and then results of our human-in-the-loop experiments. Our presentation will conclude with a discussion of our use of transfer learning and the results of our different experiments.
Locating a specific feature in a medical image, known as anatomical landmark detection, is an important pre-processing step for medical image analysis. The reason for this is that due to the variable nature of human anatomy and inconsistencies in the patient's position relative to the scanner, key anatomical features, such as organs, can be in a wide range of locations in the image. Key examples where landmark detection pre-processing is required is the identification of pathological features in brain MRI, identification of abnormalities in fetal ultrasound images, and the determination of cardiac ventricular health from abdominal MRI. Manual landmark detection, however, is time-consuming and requires expensive medically trained staff. Automating this task, however, is not trivial due to the variable nature of the human anatomy and the requirement for high reliability and accuracy. A technique which can deal with this complexity well is reinforcement learning.
In reinforcement learning, an agent operates within an environment and takes actions to maximize the expectation of future rewards. During training, the agent interacts with the environment and accumulates experience that it then uses to gradually improve the accuracy of the value function. The value function is then used to assess the available actions, and the agent uses these assessments to form a policy. In recent years, significant developments have been made in the field, most importantly with the use of neural networks to approximate this value function. Inspired by the success of these techniques, the Biomedia Lab developed a framework that uses deep reinforcement learning to locate anatomical landmarks in medical images. The datasets they've used are brain MRIs, cardiac MRIs, and fetal ultrasound scans. We have used this framework as a starting point for our project, and we also use these same datasets to carry out experiments. In this framework, states are represented by a series of 3D regions of interest centered around the agent's location. The agent can choose between 6 actions to move by fixed steps in the 3 orthogonal axes. This way, the agent navigates around the image. Rewards are represented by the improvement in the Euclidean distance from the target. Finally, during testing, termination is reached when the agent oscillates around a fixed point. So this is a summary of the key attributes that define the RL framework that we used in this project.
In our project, we made heavy use of agile working methodologies. The key methodologies that we use were sprints, scrums, and Kanban. Our sprints lasted roughly 2 weeks in length, and scrums took place at least twice a week. We used ZenHub, a GitHub plugin, for our Kanban board. As a team, we also practiced continuous integration, pair programming, and testing. We used Git for our version control system, maintaining 3 separate branches for each of the GUI, human-in-the-loop, and transfer learning workstreams in the beginning stages of the project. Our strong team working and agile approach enabled for efficient resource allocation with more team members working on the GUI development in the first half of the project and on human in loop in the second. Transfer learning, a largely independent workstream, continued in parallel. This is shown in the figure on the screen. I will now give a brief overview of the ALADDIN interface. Upon launching the GUI, a help window is shown where we have written detailed instructions for how to use each of the 3 modes. We also have a link to our repository for further information. We've implemented a menu bar with keyboard shortcuts for key actions, as well as control over the display of additional features, as shown here. There is a link back to the help window. By default, we start the GUI in automatic mode with the taskbar radio button set to evaluation. On the top left here, we have default, model, landmark, and image data. And below that is the functionality for loading custom data. This is targeted at more advanced users and those carrying out their own reinforcement learning experimentation. Kiki will now take you through automatic mode in action.
We will now demonstrate ALADDIN on automatic mode. Automatic mode allows user to visualize pre-trained agent trajectories. To start the simulation, user needs to first select a dataset. User can either use default brain, cardiac, field, or alternatively load their own custom image, landmark, and model. After selecting a dataset, user can choose between play or evaluation, where play tests agent on an unseen dataset and evaluation assess performance on annotated image. To start the simulation, press the Start button. During the simulation, user can visualize agent movement on 3 different MRI views: sagittal, coronal, and axial. Apart from that, user can also visualize agent's trajectory on a 3D plot, as shown on the white background plot here. User can change simulation speed by sliding the speed slider. Sliding to the left will decrease the speed. Sliding to the right will increase the speed. At the end of each episode, an assessment message is printed to the terminal log, as seen here.
We will now demonstrate ALADDIN in browse mode. Browse mode allows the user to interact with the GUI by moving the agent manually using these buttons here. The user can also change the step size, moving the agent by smaller or larger amounts each time. And the user can switch to the next loaded image in the batch by clicking this button here. And if the user would like to toggle between different data sets, they can do so up here as for automatic mode.
Let's now dive deeper into the technical side of GUI. GUI has 3 distinct components: the central widget, the left widget, and the right widget. All of these components are tied together by the controller and window class, which acts as GUI launcher and also responsible to instantiate core classes. All of the GUI components communicate with each other through signal and slots. GUI is coded using the event-driven programming paradigm. The central widget, also known as Simple Image Viewer, is responsible to perform main GUI visualization. This includes drawing axial, sagittal, coronal 2D plot, as well as the 3D trajectories plot. This widget also interacts with the medical player, where the latter supplies information from RL backend in real time. It is composed of plot 3D class, which is responsible to perform stuff related to the 3D trajectory plot. The right widget is a tab widget. It is responsible for instantiating and managing automatic and browse mode settings. Human in the loop functionality sits within the right widget, more specifically the right widget settings browse mode. The right widget settings browse mode comprised of XMove, YMove, setMove classes, which are used as navigation tools during the human-in-the-loop mode. As for the automatic mode, it is controlled and managed by the right widget settings. This class composed of the terminal, which log GUI commands and simulation results. Both the right widget settings and right widget settings browse mode shares the plot class, which is responsible to draw to the error plot. The left widget, known as the left widget settings class. It is responsible for tasks related to loading default and custom image, landmark, and model. Quick Help widget, which contains the textual help of the application, is also composed within it.
An algorithmic extension allowing the agent to learn from human experts was implemented. The reason why this was investigated was that by learning from an expert, the agent may learn a final solution which improves its overall accuracy in finding the landmark. Additionally, by first observing the human, the agent may learn faster, therefore increasing the training efficiency. And finally, by mimicking the expert in some manner, it may yield a more explainable policy. For example, following the arteries to the heart rather than going straight there. To achieve this, the agent samples from two sources of experience. First, the human experience replay buffer, containing transitions generated by the expert, and then from a standard agent experience replay buffer, which is populated by transitions generated through an epsilon greedy policy. The objective function is a hybrid loss function, consisting of the standard temporal difference loss, as we can see detailed here, and by a supervised classification loss, as we can see detailed here, which ensures that Q values corresponding to actions that the human did not take, being a set amount lower than Q values corresponding to actions that the human did take. The exact balancing contribution between these two is a hyperparameter which needs to be set, detailed here by Lambda.
Implementing a human in the loop was difficult as it tied together the existing reinforcement learning functionality with the GUI and additional data collection and processing requirements. In this slide, we provide a high-level description of our human in the loop implementation. We begin with the green section labeled CPU local. This is the front end of the human in the loop process, which is responsible for collecting and storing the data from human experts. This data is collected by having experts interact with the GUI in human in the loop mode. Human in the loop mode can be launched from within browse mode by clicking this checkbox here. This alerts the user that the interactions between the user and the GUI will be recorded until the human in the loop session is finished. The aim is to move the agent to the target landmark by moving with the arrow buttons. We have enabled keyboard shortcuts to make this a more efficient process. Upon reaching the target landmark, the user will switch to the next image and will repeat this process until the user has collected enough data. The data for each episode is recorded as a dictionary. Recorded data includes the states, actions, and image name. Once the expert is finished collecting data, they can end the human in the loop session as follows. The user can end the human in the loop mode session either by exiting the application or by checking this checkbox again, which will revert the GUI to browse mode and stop recording the interactions between the user and the GUI. This creates a local pickle file which logs the data for this human in the loop session. This concludes the local data collection component. Now we pass over to the section labeled GPU cluster. This part handles training the agent using human in the loop. As a pre-training step, the log files containing the human in the loop data must be assembled into the human experience replay buffer. This means changing the data into a format which can be fed into the DQ network. The neural network is then trained on the human replay buffer for a number of steps, usually 100,000 for us. Once this step is done, the usual reinforcement learning training loop begins where the agent interacts with the environment and its neural network gets updated. The agent is trained on batches containing a mixture of agent and human replay data, usually an 80-20 split. These are the key details of our human-in-the-loop implementation.
Using this process, we carried out extensive experimentation on all 3 datasets. For brain MRIs, we tried different combinations of the key hyperparameters of human-in-the-loop. These mainly affect the relative importance of the human and the agent experience in the value function. In this plot, we're looking at the performance of the agent on the test datasets at different stages during training. You can see that the bulk of the models achieve similar high accuracy and high precision with a mean distance error at around about 1 millimeter. We have successfully demonstrated faster convergence with human-in-the-loop, where the agent already achieves approximately 1 millimeter mean distance error at the first evaluation after pre-training. On the cardiac dataset, we saw significant performance improvement on the training dataset, both in terms of accuracy and speed of convergence. However, this did not generalize well enough on the test dataset, where we see similar performance to the baseline. We expect that with more expert annotations using ALADDIN, the mean distance error would also improve on unseen images. Finally, on the fetal dataset, we once again observed that the bulk of the models achieve similar mean distance error. However, there are cases where the agent does not approach the target on the test dataset. This is evident by the high standard deviation on the plot. We believe that there is a level of overfitting because we only had 50 scans available for training, and we therefore repeatedly use the same images in the human buffer. This gives you a quick high-level overview of the results of our human-in-the-loop experiments.
Parallel to developments related to user interaction with the reinforcement learning framework, the project also explored the use of transfer learning in training an agent to detect landmarks. For an agent to detect a landmark, a deep Q network is trained to predict the optimal action for finding a target landmark given the agent's current location in an image. This training process requires 40 to 50 hours of training time, even on very powerful GPUs such as the Titan XP. Medical images usually contain several landmarks of interest, each normally requiring its own independent training process. With transfer learning, we provide functionality that allows leveraging knowledge from existing models to train faster. The key functionality that we provide for transfer learning is to allow the user to select groups of variables from existing models, and also to select the groups of variables that should be optimized during training. As shown in this diagram, as default, the deep Q network is split into 2 main variable groups, one for the convolutional part of the network and one for the fully connected part of the network. Advanced users can easily define custom variable groups. This slide looks at 3 examples to illustrate the performance of the transfer learning implementation, where the first case is a baseline where training is started from regular initialization of the network parameters with the goal to learn to detect the mitral valve center in cardiac MRI scans. In the second case, an agent is trained to find the same landmark, but using transfer learning from a model trained to detect the apex point. The final case is identical to the second, except the parameters of the convolutional layers in the deep Q network are kept frozen throughout training. These results show that using transfer learning achieves comparable performance as measured by the mean distance error in detecting landmarks over a set of previously unseen images, but uses significantly less resources, with training only requiring 30 hours compared to the 44 hours of the baseline, which is enabled by the ability to only re-optimize select parts of the deep Q network when using transfer learning. In this presentation, we have introduced ALADDIN, the Anatomical Landmark Detection and Demonstration Interface. This is an integrated reinforcement learning and visualization suite for the automatic detection of human anatomical landmarks. This is a product which we believe could be feasibly deployed into a clinical setting and used by medical imaging professionals. It could also be a valuable tool for medical imaging or reinforcement learning researchers. We hope you have enjoyed our presentation, and thanks for listening.